Hello there, I'm Mr. Math Guy, and today we're going to be taking a look at a 10-minute video about arcs. In this section, we're probably going to spend the majority of our time thinking about arcs and how to find their measures in degrees. But before we get into any of that, let's review what an arc even is. If you want to remember here, we have a circle. An arc is simply a subset of a circle. So you have a point on this circle, maybe a point, and then all these points that would consist from there to there. So it's not the whole part of the circle going around. It's just maybe part of a circle. So a subset. So right there, that's a subset of the circle. So that right there, that is an arc. Now to determine the angle measure of an arc, or an arc's measure, one of the things we want to go over is an essential angle. If we take a look at the definition, a central angle is an angle in the same plane as a circle whose vertex is the center of the circle. So look right here on this little diagram that I have. If this is our center of our circle right here, you have two rays that extend to the circle, and these rays would also be considered radii. All right, each one's a radius. If you have two radii that are formed here, then this right here is called a central angle. Now, the interesting thing about a central angle, let's say this central angle is 80 degrees. If the central angle is 80 degrees, then the arc's length from here to here, that arc's length will also be the same. It will also be 80 degrees. All right, so there's a unique relationship between the measure of a central angle and the measure of its what we call intercepted arc. Now, another important angle that we're going to look at and come up on here in the next few sections is something called an inscribed angle. An inscribed angle is an angle with its vertex on the circle. So maybe we have right here, its vertex is going to be on the circle, and its sides made up of chords. So we have like here and here. That would be considered an inscribed angle. Now, there is a unique relationship between the inscribed angle and its arc that is formed, but we'll discuss that in another section. But for right now, you do need to know the difference between a central angle, which the vertex is at the center, and an inscribed angle, which the vertex is on the circle. Now, a couple other special definitions that we need to know of certain types of arcs. First, we have something called a minor arc. A minor arc, like I have drawn here, the purple arc, is an arc that measures less than 180 degrees. If you think about it, the distance all the way around a circle is 360 degrees. So if you got something less than 180, then it's considered a minor arc. And then we have something called a major arc. A major arc is an arc, for example, the orange arc that I've drawn here, that is going to be greater than 180 degrees. So it's a large portion of the circle, the points that contain the circle. And then one that is exactly 180 degrees is called a semicircle. So, for example, the green. You can see that if I were to connect from the end of this arc all the way over to the end of this arc, then that creates a diameter, which is exactly, and the arc distance would be exactly half of a circle. So we call this a semicircle. So here are three definitions of arcs that you need to know. A minor arc, less than 180 degrees. A major arc is greater than 180 degrees. And a semicircle is exactly equal to 180 degrees. Now let's take a look at a very important postulate, one that you'll see over and over and over again. That's called the arc addition postulate. And it says if you have a point B that is on arc AC, then the measure of AB, arc AB, plus the measure of arc BC is equal to the measure of arc AC. So up here you can see that B is on this arc. If it's on the arc, then the distance from A to B, here to here, plus the distance from B to C, here to here, is equal to the whole thing, A to C. Which brings us to a theorem here. It's called the major arc theorem. It's pretty easy to understand. It simply says that the measure of arc ACB, now you have to follow the arc the way it's written. So ACB would be from here all the way around this circle to there. That's measure of arc ABC. It's going to be equal to 360 minus whatever, excuse me, here it goes all the way to B. It's going to be equal to 360 minus whatever AB is. So if AB, let's say, is 10, then ACB is going to be 360 minus 10, or 350. That's because the distance all the way around the circle with the measure is 360 degrees. Now, I've listed a definition and 4 biconditional theorems. We're going to take a look at these. Congruent arcs are arcs on congruent circles that have the same measure. So if you have one arc measuring 40 degrees on one circle, and you have another arc on a congruent circle measuring 40 degrees, then these arcs are said to be congruent. First theorem, chords of congruent circles are congruent if and only if, so it's biconditional, it works both directions, if and only if they subtend congruent arcs. So if you look down here, the purple chords are going to be congruent if the arcs that form these are congruent. So if this part and this part, those arcs are the same, then the chords will be the same, and vice versa. The next theorem says in congruent circles, chords are congruent if and only if the corresponding angles are congruent. So if both angles are, let's say, 5 degrees, which it's bigger than 5 obviously, but if both of the corresponding angles are congruent, then the chords are going to be congruent. And it works the other way around too. If the chords are congruent, then the corresponding angles are congruent. So in the previous theorem, if the congruent arcs are the same, then the chords are the same. This one's if the central angles, corresponding angles are the same, then the chords are the same. The next theorem says in congruent circles, minor arcs are congruent if and only if their corresponding central angles are congruent. So going back to this one over here, the red part, these minor arcs are congruent if their central angles are congruent. And then the next theorem, in congruent circles, 2 minor arcs are congruent if and only if the corresponding major arcs are congruent. So if this part, let's just say, is 200, and this part right there, let's just say, is 200, then the minor arcs must be the same. They would both be 160, using your major arc theorem to show that the minor arc would be 160 because the whole thing is 360. So let's take a look at an example problem. Let's say we have 2 congruent circles, circle P and circle Q, and let's say we have that the measure of angle APB, so APB is equal to the measure of CQD. So this angle right there and this angle right there are congruent. And let's say that we know that AB is 12. So this chord right there is 12. Then what is AD, this chord? Well, this one's going to be pretty easy. It's going to be 12 as well. CD is going to be 12. The length of chord CD will be 12, since the length of the other one is 12. And the reason that we know that is true is from our previous theorems, because our theorem says, hey, if the central angle is congruent to another central angle, then its chords are going to be congruent as well. So if one chord is 12, the other chord will be 12. Let's take a look at a couple other examples. Let's say that we have to find the measure of arc BD. Well, first of all, you have to think, oh, measure of arc BD, which direction are we going? Well, if you look at the next problems, BAD. So BD is just a minor arc. Usually if it's a major arc, well, almost always if it's a major arc, it'll have 3 points, so you know which direction that it's going in. This is BD, so this is the minor arc, and we're going to use our arc addition postulate. So 50 plus 40 then is 90 degrees. Now, if that part is 90, then 360 minus 90 is 270 degrees. Hope this video helps. Thank you for watching. God bless.